Alright, this is the third and final video on oxygen nucleophiles. In this video, I'd like to talk about using cyclic acetals as protecting groups, and then we'll talk a little bit about hemiacetals. So one thing we've mentioned a couple times in this chapter is that these nucleophilic addition reactions are equilibrium processes. And so depending on the reagents and the products and the conditions, we can favor either the reactants or the products, and we can control this very often using Le Chatelier's principle. And so we're going to use that feature of these reactions for something that's called protecting groups. And this is similar to in the last chapter when we had the reversible sulfonation reaction and we used it to make blocking groups. In my mind, protecting groups are somewhat similar to that. And so we can control whether the ketone, or in this case the cyclic acetal, is favored by controlling the amount of water. So if I take water away from the reaction, I can favor the acetal. If I add water to the system, then I can go back to favoring the ketone. And so let's see how that applies to protecting groups with the next example. So let's imagine we wanted to do this synthesis. So I want to convert this compound into this one. And so I want to convert this ester into a primary alcohol, but I want to leave the ketone alone. So that's our goal, to convert this ester into this alcohol. Now the way to do that is to use lithium aluminum hydride, and that will take my ester and convert it into the alcohol. The problem is the lithium aluminum hydride is also going to reduce the ketone. So if I just add LaH to this, I'll convert both of these into alcohols. And I don't want to do that. I want to leave the ketone alone. So the solution to this is I can use a cyclic acetal to protect this ketone. So here's what that would look like. First, add a diol, right? An alcohol with two OHs. Do it under acidic conditions, take out the water, and I'll form this cyclic acetal. Now, when I add the lithium aluminum hydride, it can't react with this acetal, but it will react with our ester. So when we add the lithium aluminum hydride, it will reduce the ester like I wanted to, leaving the acetal alone. I can then add water back in with an acid catalyst, and I can convert the acetal back into the ketone. And so that's what we use the protecting group for. We're using it to protect this functional group. And the key thing, both in the blocking groups that we saw last chapter and with the protecting groups this chapter, we need reversible processes in order for these to work. Because once I react away the ketone, I need a way to get it back. So I need a reversible equilibrium process. All right, and then just a word on hemiacetals. We haven't talked a whole lot about those, other than as being intermediates in the mechanism. And the reason that is because they're generally difficult to isolate. Usually the equilibrium either favors the ketone or the acetal, and it's very difficult to find conditions that will favor the hemiacetal, which is why we haven't talked about it a whole lot. With one exception, cyclic hemiacetals are fairly easy to isolate. So, as I just said, cyclic hemiacetals can usually be isolated. And so this will happen when we have an alcohol as part of the same compound as the ketone. And so they then form this cyclic hemiacetal, which are favored at equilibrium. And we don't spend a lot of time on carbohydrate chemistry in this chapter. But if you're a biology major, particularly a biochemistry major, and you go on to take biochemistry, you'll talk a lot about carbohydrates. And so we can draw carbohydrates as straight chains or as cyclic hemiacetals. And in fact, under solution conditions, it is these ring structures, these cyclic hemiacetals, that are the preferred configuration for glucose and many other carbohydrates.